All right, here is our notes on common ions and buffers. And for this, you're going to need your calculator, and you're going to need to write and think about what we're doing here and how this all relates to the equilibrium and the acids and bases that we've been talking about so far. All right, the first section is the common ion effect. And the first part says solution number 1 contains 16.4 grams of sodium acetate dissolved in a 1 liter volume of water, and asks us to compute the number of moles of sodium acetate. Straightforward, divide by the molar mass and we get 0.2 moles. Now, sodium acetate is a completely soluble ionic compound, so is it a weak or is it a strong electrolyte? Well, obviously it's a strong electrolyte, which means it dissolves 100%. So the concentration of the sodium ions in this solution is going to be equal to the same 0.2 molar because I've got 1 liter. And the concentration of acetate is also going to be equal to 0.2 molar. Now we have a different solution. Solution 2, it's acetic acid, 0.2 molar acetic acid. And the Ka for this weak acid is 1.8 times 10 to the minus 5th. And we know that it's a weak acid because it's not on our list of strong acids and because I've given you the Kb. Therefore, it is a weak electrolyte, and we need to write the Ka expression for the acetic acid. And this is pretty straightforward from our study of equilibrium and our study of acids and bases. All right, now, the third part here is we need to calculate the hydronium ion concentration and the acetate ion and the pH of this 0.2 molar acetic acid. And we set up our equilibrium conditions. We let X equal to the unknown amount of hydronium ion and acetate. And we assume that X is so much less than 0.2 that we can ignore it. When we do, we get X is equal to 0.001897 or 1.9 times 10 to the minus 3. And when we take our pH, our negative logarithm of that number, we get 2.72. I strongly urge you at this point to get your calculator and make sure you can do this. All right, solution number 3. Now we're mixing 500 mils of solution 1 and 500 mils of solution 2 to get a total volume of 1 liter. And we need to fill in the Rice table. So we've got our reaction, and we know our initial conditions. The molarity of the original solution was 0.2, but now it's 0.1 because I've diluted it by mixing it 50-50 with the other solution. All right, so our change is going to be minus X, and plus X, leaving us with this as our equilibrium condition. And we can ignore X compared to Ka, and therefore we can assume that really 0.1 plus X is 0.1 and 0.1 minus X is 0.1. And so what's the concentration? Well, we plug in our K values and set up our equilibrium, and we get this. So X is equal to 1.8 times 10 to the minus 5, and that's our hydronium ion concentration. And therefore the pH of this solution is equal to 4.74. That also represents the pKa, the negative logarithm of the Ka, of acetic acid. All right, now we want to write the value for our hydronium ion solutions for the second and the third solutions. And we see that we had 1.9 times 10 to the minus 3 and 1.8 times 10 to the minus 5. Now, why are they so different? Well, we can talk about this when we talk about what we call the common ion effect. I have a weak electrolyte, in my case, or our case, acetic acid, and I have a strong electrolyte, or sodium acetate, and when they're together in a solution, the weak electrolyte ionizes less than it would if it were alone in the solution. And we can also look at this from Le Chat's principle. All right, so we've got our acetic acid plus our water is in equilibrium with H3O plus an acetate ion. And if additional acetate ions from the sodium acetate are added, we of course are going to get a shift back to the left. All right, this decreases the amount of H3O plus, and therefore the pH value is going to go up. All right, next problem. A student's given a solution of 0.2 molar HF and then adds a few drops of 12 molar HCl to this HF solution. The question is, what's going to happen to the value of H3O plus after we've added the HCl? Well, it's going to go up a lot, right? HCl is a strong acid, and at 12 molar is a very concentrated strong acid. So H3O plus goes up remarkably. What happens to the value of the fluoride ion after the HCl is added? Well, it's going to decrease because what I've got here is a common ion effect. And the addition of the hydronium ion is going to shift this whole equilibrium to the left, which lowers our fluoride ion concentration. Now we can get this in both weak acids and weak bases. So now we're going to do a problem with a weak base. We've got a solution that's 0.2 molar ammonia, and the Kb for this ammonia is 1.8 times 10 to the minus 5. Now you'll note that that's the same numerical value as the Ka for acetic acid. That is a coincidence. These are not related to each other. It just so happens to have the same number. So we want to write the Kb for ammonia. Of course, we can do that. We can say the Kb, K for the base, is the ammonium ion times the hydroxide ion divided by the ammonia concentration. And we want to calculate OH minus, NH4 plus, and pH of this 0.2 molar ammonia solution. Well, we can set up our equilibrium expression, and we've been down this road a lot. We know we can ignore certain things with regard to the Kb, and we end up getting X is equal to 1.9 times 10 to the minus 3, same numerical value because it's the same numerical value of the K. So the pOH is 2.72, which gives us a pH of 11.28. Now, what would happen if we added ammonium chloride to this solution? Well, that's going to make the concentration of the ammonium ion increase, but it's going to make the concentration of the hydroxide ion go down. And again, we can look at this by Le Chat, and we can see that if additional ammonium ions from ammonium chloride are added to this solution, we are going to get a shift to the left. All right, now, question K, or part K. A solution is prepared by mixing half a liter of 1 molar ammonia with half a liter of 1 molar ammonium chloride. We get a total volume of 1 liter, and we're going to fill out our rice table. All right, now again, we do the same thing. The concentration's cut in half because now we've diluted it. And so we have minus x, plus x, plus x, 0.5 minus x, x, and 0.5 plus x. And we can make the same simplifying assumptions that we have in all the others because the value of Kb is pretty small. So we see that when we solve for the concentration of the hydroxide ion in this solution, we end up getting, we solve for x, which is our OH minus, and we get 1.8 times 10 to the minus 5. And the pOH of this solution is equal to 4.74, which also represents the Kb. And the pH of this solution will be 14 minus 4.74, or 9.26. So far, this is not very surprising to us. It's just a little bit different application of the concepts that we've already gotten used to. All right, now we're going to talk about a buffered solution. A solution that contains a weak conjugate acid-base pair. It's called a buffered solution because they can resist a drastic change in pH. All right, now part B asks us to circle out of these 8 solutions which would represent a good buffer. Now look back up to the top. To determine what's a good buffer, we need a weak acid or a weak base and its conjugate pair. All right, so when I look at these 8 solutions, I'm going to end up with these 4 choices. Now, let's justify these in part C. A buffer has to be a weak acid with its conjugate base or a weak base with its conjugate acid. Now, let's look more about the choices that are not circled. So HNO3, not a weak acid. Therefore, it's not a good choice for a buffer. When I look at choice 3 on the left side, again, HClO3, it's a strong acid. Therefore, it's not going to make a good buffer. Now, in the 4th choice on the left side, I've got a weak acid, all right, acetic acid, but now I have sodium carbonate. So the carbonate is not the conjugate base of this particular weak acid. Again, I look over on the right-hand side, and the 3rd one down is the one that I haven't circled. I have methylamine, which is a weak base, but then I've also got acetic acid. These two are not conjugate pairs of each other. Therefore, they will not make a good buffer system. All right, now, part D says the expression for this acid dissociation constant for this weak acid is written as this. Ka is going to be the concentration of H times the concentration of A minus divided by HA. And I want to rearrange this expression and solve it for the concentration of hydronium ion. I can do that by multiplying both sides by HA and dividing by A minus. And when I do, I get this, just a simple algebraic rearrangement. Now, this equation that we just wrote is called the Henderson-Hasselbalch equation. And from this, we can see that H plus and pH are determined by 2 factors. It's the value of the Ka for the weak acid HA, whatever A happens to be, and some ratio of the concentrations of HA and A minus. Now, in this figure in the above right of this slide shows a diagram which represents the buffer solution. All right, in this initial buffered solution, which is the center of the diagram, the blue F minus and sort of the tan colored HF, the concentration of HF is equal to the concentration of F minus. And it says that right above the sort of the horizontal tiled area of this, all right? Now, suppose we add OH minus to this buffered solution. We want to write the net ionic equation that would occur. Well, I've got HF plus OH minus, and that's going to react to form F minus plus H2O. Now we add OH minus ions to the HF and F minus buffer. It's going to cause the concentration of HF to go down and the concentration of F minus to go up. Now, suppose we add H plus ions to this buffered solution. We want to write another NIE. So now, if I have F minus plus hydronium, that's going to form HF. So adding H plus ions to this is going to shift our equilibrium to the right. HF will increase and F minus will decrease. And as long as this ratio doesn't change very much, the pH change is going to be really small when either H plus or OH minus ions are added. And that's what makes a buffer a buffer. This ability to resist a pH change. And with that, we're going to conclude our first video.